So, the ideal source for atomic emission spectrometry should have the following properties. One is temperature should be high enough, that means the plasma should be very stable. Okay. The temperature should be high enough for all the elements you want to analyze must be excited to the next higher energy level, that is what it means. Okay. That is a universal applicable principle. So, second thing is background intensity should be as low as possible for high detectability. The temperature should be uniform and the optical density should be low for linear calibration curves. So, the rate at which the sample is acceptable should be reasonable. That means, the representative subsample should be taken in an acceptable time within the time it takes to transport. So, the sample should be acceptable as solid, liquid or gaseous forms. Introduction of the sample should not drastically alter the internal energy of the source, that is plasma source, or its supply. That means, the plasma should be very stable. All the sample material should be converted into free atoms within the source, and the source would operate on commonly available reasonably priced gases, that is argon only as far as our experience is concerned. So, the ICPE comes close to fulfilling these specifications for an ideal source, because the temperature is high enough and majority of the elements can be determined. Background is really low, because the ICP optically it is almost transparent, the plasma. The temperature is fairly uniform and the tail flame is optically thin. That means, not much emission coming from the tail flame. The background would be very less, sample is acceptable in all the forms. Okay. And the sample input through the peristaltic pump is acceptable at a reasonable rate. The introduction of the sample does not seriously affect the energy. For gaseous and liquid samples, the material is converted into atoms and the plant operates on the argon, which is freely available at a reasonable price. So, it has the advantages. One is rapid and simultaneous multi-element analysis. It is an excellent source of atomic emission, that it is optically thin. Calibration curves are linear over 4 to 6 orders of magnitude also. Detection limits are very low, the 1 to 100 nanograms or microgram per liter, that is parts per billion, and it is suitable for analytes at all concentrations from trace to major levels. Accuracy and precision are very good. In principle, ICP-AES can be used for the determination of all elements except argon. That is understandable, is not it? So, in practice, practically about 70 elements can be determined using ICP-AES with one single source, that is plasma. So, elements that are difficult to determine by AAS can be determined easily. For example, boron, carbon, cerium, lanthanum, these are rare earth elements, and then actinium elements, and then many of them are refractory elements like titanium, tantalum, vanadium, zirconium, etc. So, now I want to talk to you about a little bit about the analytical aspects, because any chemical analysis must follow certain analytical rules, and these are for analytical scientists, these are all sort of understood, but for students it is better to understand a little bit about the fundamental principles of chemical analysis. So, here we talk of several systems, and I want to define certain solutions, certain terms for your easy reference, because whenever we talk of chemical analysis, the technical terms we normally use, technical jargon, should not be confusing to non-professionals. For example, many of you who are taking this course may be students or may be officials, may be professionals, but not trained in analytical science, but you may need the results anyway. So, this is the reason. So, the reference what I am giving you is the International Union of Pure and Applied Chemistry, that is IUPAC. You can see the slide now, and International Organization for Standardization, that is ISO 6955, that defines the analytical spectroscopic methods for flame emission, atomic absorption and atomic fluorescence. So, the solid samples can be directly analyzed by AES, but the majority of the samples are presented as liquids or solutions. Now, what is a sample solution? It is a solution suitably made up from a test portion of the sample submitted for analysis. That means, it is the solution to be aspirated into the ICP. What is a stock solution? A solution of known concentration from which the dilutions are made to prepare the calibration standards. Okay. Then comes reference solution. These are what we prepare known concentrations from the stock solutions. So, from the stock solution is, suppose you have 1 ppm here, 1 gram per liter, that is approximately 1 milligram per milliliter, that is 1000 ppm, but you do not need 1000 ppm, you may need only 1 ppm, 10 ppm, 50 ppm. So, these concentration, these solutions prepared from the stock solution are known as reference solutions. So, a series of known concentration of the analyte element in a solvent is known as reference solution. It may contain the matrix elements also. Okay. So, a blank solution. So, blank solution is a 0 member compensation solution containing all other elements, that is matrix matching in the same solution, but it does not contain the analyte. So, blank solution should be having 0 concentration of the analyte. Okay. And analytical curve. So, what it means? It is the calibration curve or a graphical plot of the measured absorbance or emission or to the concentration or mass of the analyte sample. So, it is the, this is the curve what you need for chemical analysis, interpretation of the results. So, what is a characteristic concentration or characteristic mass? So, this refers to the concentration of the analyte element corresponding to a net absorption or emission of 1% or an absorbance of 0.044 when integrated absorbance or peak area is used. So, we can take the almost the same for emission ICP AES also. Okay. So, sensitivity. So, it is the slope of the analytical curve that is termed as sensitivity. It is delta A by delta C or delta A by delta M. C, delta C is the concentration, delta A is the absorbance or emission. So, change in the emission or absorption with respect to concentration or mass is known as the sensitivity. So, for good sensitivity, change should be large for small concentration change. So, accuracy. Accuracy relates to the closeness of the agreement between the true value of an element in a sample and the mean value. Usually true value is not determined, is not determinable, but mean value is determinable. So, it can be calculated by the difference between the true value and the measured values, where there will be some slight difference, and the difference should be as low as possible compared to the true value and mean value. So, precision. Precision relates to the closeness of the agreement between the results obtained by applying the analytical procedure repeatedly. Suppose you do three different analyses using the same set of conditions. If the results match, then we say results are very precise, but the results it does not mean results are correct. Okay, because the same error could have been carried out in all the 3 samples. So, precision does not guarantee accuracy, but precision means the system is perfect. So, it is determined by multiplying the standard deviation sigma with 2.83 for 30 or more measurements, or T dot sigma, T into sigma, where T is the student's factor. You should look up a little bit about student's factor in your analytical books to find out what is exactly T student factor is. Student is the name of the scientist. So, we also have some of these terms you come across regularly, that is standard deviation. It is given by square root of x y minus x bar whole square divided by n, where x bar is the mean value of all measurements and xi is the individual measurement, n is the number of measurements. In standard deviation, what we mean is the actual analytical value is spread over the mean value plus or minus some number. Okay. So, it is a very important concept in all analytical measurements. So, relative standard deviation is can be calculated by dividing standard deviation by the mean value. Okay. So, the determination limit, this is the lowest concentration that can be determined with the prescribed precision for practical procedure. That means not detected, it is determined. That means quantitative determination is involved here, not just the present yes or no, it is not that type. Okay. So, detection limit is delta C by delta A into k dot sigma, or delta m by delta A into k dot sigma, where k is the factor k is 2 or 3 and sigma is the absolute standard deviation. So, the detection limit what I have shown you earlier in the table are these numbers. Okay. So, it is the detection limit can be measured either using peak area or peak height, that is the emission line spectrum. Both are functions of electrical noise, optical noise, sensitivity, metastable energy status of the analyte element and the chemical element environment, that means that is matrix matching. So, the detection limit can vary for different systems. I hope you are understanding what I am trying to tell you are the different analytical aspects, jargons what we normally come across. So, it should be evident to you that the reliability of a measurement depends upon all these factors: detection limit, standard deviation, relative standard deviation and all that, slope, sensitivity. We should be able to determine all these things. So, I have a figure here for you that makes a difference here. For example, this is the mean background signal. Okay. Here is the intensity signal, number of counts. This is without putting anything your sample, the signal goes like this, and above this, 3 times above this, the average value of the mean background signal is the limit of detection, and intensity signal limit of identification. So, we can say if you get a signal around this level, I think there may be element may be there, but to make it sure that the element of analysis is there, we have to go to higher level, that is known as limit of identification. So, if you get a reading like this, it means the element is definitely there. Okay. And if you, how much is there is gives you the limit of determination. So, above this, if you get a reading anywhere around this region, the determination is possible. So, you have to understand that this is not done according to scale, because I will have to define all the k sigma and 2.3 student T factor and all those things. Okay. So, the determination limit that can be determined with the prescribed precision for the analytical procedure. And now, I will tell you a little bit about calibration technique. So, AAS is the relative technique and not an absolute technique. AES also is a relative technique, but not an absolute technique. This means that quantitative result can be obtained by comparison with reference to solutions or reference materials. Therefore, reference measurements must always be made. Different calibration techniques are available to meet the analytical requirement, and I have also told you that internal standards need to be employed in AES. So, the analytical curve technique, bracketing technique, analyte addition technique, all these things can be employed to determine the concentrations of the samples. So, the wide dynamic range of ICPS is certainly impressive. Calibration graphs are essentially linear below 10 ppm and even up to 1000 ppm, that is stock solution itself can be measured if the sensitivity is low. So, as we have noted previously, this is not only desirable attribute of the technique, but it is essential for us if the full potential of simultaneous analysis is to be exploited. So, sometimes what happens is we need to extract and enrich the sample and separation. So, insufficient sensitivity is one of the reasons. Faced with such a problem, a more sensitive method needs to be employed, and in trace and ultra trace analysis, every sample pre-treatment is a potential source of contamination. We have to be very careful, and if separation and enrichments are time consuming, they do demand a degree of knowledge and skill. This is where the chemical ingenuity of the person performing the chemical analysis comes into play. So, in trace and ultra trace analysis, every sample source is a sample pre-treatment should be a source of contamination. As far as possible, we try to avoid. That is the reason we try to give it a introduce the sample as it is. So, among the techniques used for separation and enrichment of the analyte solvent extraction, activated charcoal method, electrolytic decomposition, etc., are prominent. I will not go into details of these, but these things are available in the literature and the reference books. So, we also use chelating agents such as EDTA, ammonium pyrrolidine dithiocarbamate and nitrilotriacetic acid, etc. These are used to complex many metals over a wide pH range, followed by extraction into MIBK or methyl butyl ketone or any other solvent known to facilitate trace analysis. So, pre-concentration with activated charcoal is very well known example of enriching the analyte. Quite often the samples need to be dissolved in acids under pressurized atmosphere. This is also a potential source of error. Any sample treatment for that matter can be a potential source of an error if we do not take the proper precautions. So, ultra pure water and acids need to be employed for the analysis as well as in parts per million or parts per trillion level. It is for AS as well as ICP. Among the techniques used for separation and enrichment of the analyte sample, solvent extraction, etc., are prominent. So, chelating agents I have already referred to that, and pre-concentration with activated charcoal. Now, I will spend some time about specific applications of atomic emission spectrometry. Okay. So, here is a list of about 10 areas: the determination of calcium, magnesium, sodium, potassium, body fluids and tissues. So, tissue samples must be wet and dry ashed before analysis. Nowadays, aluminum is also an element of focus in the brain tissues owing to Alzheimer's disease. In addition, in biological applications, body fluids, arsenic, mercury, cadmium, selenium, thallium, etc., are of importance. So, in food and drinks, we have animal products such as ghee, butter, etc., cheese. Preparation, storage and metallic elements are present in many of the foodstuffs. So, functional groups attached to tissues, they need to be digested with nitric acid. They have to decompose basically. Nitric acid does that job, and almost all dairy products must be wet ashed before analysis. Lead is a very common contaminant in foodstuffs. great emphasis is being laid on the analysis of lead. Tin is also added to plastic foils. So, soil, fertilizer and plants, sodium, potassium, calcium, magnesium, copper, manganese, zinc, boron, all these elements, arsenic, cadmium, lead, all these are of importance in the soil analysis for using ICP AES. So, water, we determine almost all elements in water, and sometimes we use APDC and MIBK for concentrating the elements of interest. So, many other extraction systems have also been perfected over the years. The details are available in the standard textbooks. So, for sediment digestion we need HF and aqua regia, HF for silica and aqua regia for difficult to dissolve the samples, metals. And in the environment, it covers a whole range of factors that influence our lives. It is almost impossible to pick out any specific area in isolation, since all factors influence each other mutually. So, here is a list of possible interactions, and in the general world. So, for example, you can see that many of these are all equilibrium reactions. From the air we have humans, we breathe in and take the elements, and then commodities, they are there, drinking water, food stuff, plants, animals, surface water and subterranean water, waste water, garbage and soil. I suggest you study this cycle very carefully, because I may ask you in the examination what kind of interactions are possible in the environment. So, this is a same picture, I have drawn it slightly better so that your understanding should be proper. So, a majority of the particulate matter in the air originates from natural sources, dust and aerosols of 2.5 micron size enter our lungs, they deposit in our lungs, and they are not harmless either, they are very harmful. So, stock gases are known to carry particulate matter even up to 400, stack gases up to 400 kilometer. Suppose you have a factory that is spewing out smoke, the smoke components can be carried out up to 400 kilometers away also. So, the air pollutants are normally found everywhere, you cannot escape the polluted air. So, most of the coal gas fired pollutants get enriched in the flue dust. Treated gases, cadmium and lead are collected by filtration techniques to determine in the effluents or emission gases. Particulates are collected over 4-hour time and sometimes 6 hours, sometimes 24 hours depending upon the requirement, and toxic heavy metals including mercury are passed on to soils, surface water, etc. and sewage, sludge and electronic commodities require digestion anyway. I have already covered what kind of digestion we should be doing, the using Parbaum and other method, wet ashing techniques, etc. Anyway, digestion is a very important concept in almost all atomic emission techniques. So, calcium in rocks and minerals, of course, ICP was developed mainly for the analysis of rocks and minerals in ores. So, calcium, magnesium, potassium, iron, copper, zinc, etc. in various rock samples, gold, aluminum, platinum, many of these elements have been used, and ICP, AES and hydride techniques have substantially contributed to the determination of trace elements. So, digestion with HF and sulfuric acid is the most preferred technique for minerals. For volatile elements such as mercury, cadmium, etc., what we need is pressurization using Parbaums. The use of common fusion procedure using sodium carbonate, sodium bromide followed by dissolution of the melt in acid molybdate solution is well known. You can look up the details whenever there is a need for you to analyze by ICP dissolution. So, gold is usually extracted and enriched before determination because of its concentration is too low for direct analysis. And metallurgy and plating, aluminum, vanadium, titanium, chromium, niobium and all these elements are usually determined, especially if you want to determine plating solutions, HCl HNO3 treatment is a fairly suitable technique. So, ICP-AES is suitable for trace elements bismuth, lead, selenium, tellurium, thallium and tin in complex nickel alloys, and Bell has investigated the determination of cadmium, chromium, copper, iron, magnesium in aluminum alloys. They dissolve the alloy simply in 1:1 HCl, not more than that, with the addition of few drops of H2O2. So, oil, coal and petrochemistry I have already covered quite a lot in wear metals, and it is particularly useful for the elements of trace analysis in oil and petroleum products. Iron and copper are the additives in the lube oil, which are monitored quite regularly in ppm quantities by flame or ICP-AES. Lead in petrol is the favorite topic of all environmental analysts. Plastic, paper and textiles required. Iron, aluminum, manganese, titanium, silicon, antimony, lead, tin, zinc and many of these things are determined in plastics nowadays, and polypropylene, nylon 66, polystyrene, PVC, all these polymers are dissolved in MIBK, cyclohexane, formic acid etc. and aspirated directly. So, insoluble polymers are digested, they need to be digested anyway and bring them in solution. Packing materials may contain organotin compounds and as stabilizers, and metal plastic sample is extracted with 3% acetic acid and heptane, ethanol etc., and the extracts are determined directly in ICP-AES. That is why I keep on telling you that matrix matching is a very important concept in ICP-AES. Otherwise, there is no way we can determine such elements in such low concentrations also. For example, Langmuir has determined cadmium, copper, lead and manganese in paper, pulp, cellulose. Such small the concentrations would be less than parts per trillion anyway. That is why their work in such matrices is very well known. So, pharmaceuticals, miscellaneous products, industrial products, quite a few elements are of importance: sodium, potassium, calcium, arsenic, cobalt, manganese, silver etc. The samples need to be dissolved or leached in concentrated HCl and aspirated directly. Cobalt in vitamin B12 and proteins can be determined by the flame AES as well as ICP-AES. Barium can enter from the gloves or rubber components in addition to direct ingestion. So, direct diet supplements are routinely checked for arsenic and selenium. So, uranium in yellow cake is usually determined by ICP-AES, and these are the radioactive elements now. So, many other elements like lead, magnesium, iron, potassium, cadmium, copper are routinely determined in rubber seals, radioactive elements, and many of these things ICP-AES is the panacea. The available literature up to date is the proof of its vivacity only. So, here is a typical flow chart showing the methodology for a typical ICP. How do you go about actually doing the analysis? First, prepare the samples and standards, and then find out is there a ready made method for measuring the wavelength for measuring the concentration. If it is there, you have to tell the computer to recall the method and put all the parameters in place, and then you aspirate your calibrated samples using standard solutions and then run the samples, generate the report. So, this is how the normal scheme of chemical analysis using ICP is run. So, suppose there is no method, then what do? Then we will have to select the element or find out what are the elements find out the select elements and then collect the representative spectra, select integration time, data acquisition mode and standard concentrations, etc. Select the background, store the method and then go back to developing a method using this technique. Come back here. So, this is how an atomic ICP AES looks. Nowadays, it can be it can be put on a bench top, and it is a very simple instrument to operate, but of course, I am not showing you the gas arrangement, that is argon gas arrangement, etc. On the right side you can see the plasma here, where there is a toroidal space and the sample comes through from the bottom and the plasma is that area is somewhere here. Okay. This is only a blow up of that. So, I would like to thank you for your attention during all these 10 plus 1 lectures, during all these lectures, and I hope I have given you a sort of preliminary introduction to the technique of ICP AES. So, if you need more information, you can refer to the textbooks and other reference material I have already taught you, I have already told you. And if you need any additional information or any help, you can always contact me, and my details I have given in the first lecture of this course. So, I wish you all the best. Thank you very much and may God bless you.